What do the smell of fresh spearmint, the sharp sting of vinegar, and even a common painkiller like ibuprofen all have in common? Well, they all belong to this huge, really important family of molecules called the carbonyls. So today, we're going to meet the key players, learn how chemists can tell them apart, and uncover this amazing 3D twist in their structure that, believe it or not, can have life or death consequences.
So here's what we've got lined up. First, we'll get properly introduced to the core members of the carbonyl family. Then we're going to play a bit of chemical detective and learn the tests that are used to figure out exactly who's who. After that, we'll see how they're made and how they react to make other things. And we'll wrap it all up by uncovering a hidden secret in their structure that explains something wild, like why two molecules that look identical can smell completely different.
Okay, so let's start at the very beginning. What actually makes a molecule part of the carbonyl family? Well, it all comes down to one single, crucial feature. You can think of it like their shared family DNA.
And here it is. This right here is the heart of the family, the carbonyl group. It's just a carbon atom with a double bond to an oxygen atom. And this simple little C double bond O is the foundation for a whole bunch of compounds. But for today, we're zeroing in on the big three: aldehydes, ketones, and carboxylic acids.
First up, we've got the aldehydes. Now for these guys, it is all about location, location, location. The defining feature of an aldehyde is that its carbonyl group is always, and I mean always, sitting right at the end of a carbon chain. That gives it the functional group you see written as CHO, and we give them names that end with L, like ethano. Next, meet the ketones, and they're the perfect contrast to aldehydes. So if an aldehyde's carbonyl group is at the end of the line, a ketone's is always stuck somewhere in the middle, kind of sandwiched between two other carbon groups. And their names, fittingly, get an "-one" suffix, like in propanone.
And rounding out our main trio is the carboxylic acid. This one's a little different. It's kind of like a hybrid. It's got the carbonyl COO group for sure, but that exact same carbon is also bonded to a hydroxyl, or an OH group. This powerful combination, which we call the carboxyl group, is what gives these molecules their acidic kick and that oic acid name, like in ethanoic acid.
So, you might be wondering, how do these differences actually affect things in the real world? Well, just look at their boiling points. It all comes down to how strongly the molecules can stick to each other. Alkanes, they have only these really weak forces called van der Waals, so they boil at super low temperatures. The polar C=O in aldehydes create stronger dipole-dipole attractions, which bumps up the boiling point. Alcohols can hydrogen bond, which is even stronger, so their boiling point is higher still. But the carboxylic acids, they are the undisputed champions. They can form two hydrogen bonds with a neighbor, creating what's called a dimer. It takes way more energy to pull that pair apart, giving them the highest boiling point of the whole group.
All right, so we've met the family. But let's say you've got a test tube with an unknown carbonyl compound. How in the world do you figure out which one it is? This is where chemists break out their chemical fingerprinting kits.
Two of the most classic tests are toluenes and phthalings. And here's the trick. They're both designed to react with aldehydes, but they completely ignore ketones. If you warm an aldehyde with toluenes reagent, you get this beautiful, unmistakable silver mirror coating the inside of your test tube. With phthalings, the blue solution transforms into this solid brick red material. So if you see a change, you've got an aldehyde. If nothing happens, it's probably a ketone. Simple as that.
Now, what if you need a more specialized tool? The iodoform test is like a heat-seeking missile. It's not just looking for any carbonyl, it's hunting for a very specific structure. A methyl group, that's a CH3, attached directly to the carbonyl carbon. If that structure is there, adding some iodine in an alkaline solution will trigger a reaction that produces this pale yellow solid with a really distinct antiseptic smell. It's a fantastic way to pinpoint specific types of ketones.
Okay, this is all great. We can tell aldehydes and ketones apart. But we're still stuck, right? These tests don't tell us the difference between, say, propanol and butanone. We need a way to get a unique fingerprint for the exact molecule that we're dealing with.
And the solution to this is a reagent called 2,4-DNPH. And this is just incredibly clever. It reacts with pretty much all aldehydes and ketones, and it forms a bright yellow or orange solid. But here is the genius part. Every single carbonyl forms a derivative with its own completely unique, incredibly precise melting point. So the process is simple. You make the solid, you purify it, you measure its melting point, and then you just look it up in a data book. It's like a perfect fingerprint match to identify your original mystery molecule.
So now that we know how to identify them, let's look at what they can do. How are these molecules actually built in the lab, and how can we use them as building blocks to create other really important compounds?
A really common way to make them involves what we call the oxidation ladder. Think of it like this. You start on the ground floor with a primary alcohol. If you gently oxidize it, you climb one step up the ladder to an aldehyde. But if you want to keep going, you can use stronger conditions and more heat to climb all the way to the top and form a carboxylic acid. It's a really controlled way to move between these compounds.
Carbonyls are also absolutely essential for making esters. You know, the compounds that give fruits and perfumes those wonderful smells. And there are basically two ways to go about it. You've got the slow and steady traditional route, esterification, where you react a carboxylic acid with an alcohol. It works, but it's reversible. Then there's the fast and furious route, using an acyl chloride instead. That reaction is way more energetic and it goes to completion. But there's a trade-off. It produces nasty hydrogen chloride gas as a byproduct.
Now here is a quirky but really important little detail in carbonyl chemistry, and it all comes down to this number, 2. Whenever you react an acyl chloride with something like ammonia or an amine to make an amide, you always need 2 molecules of the amine for every 1 molecule of the acyl chloride. So why 2? Well, the first one does the main job. It makes the product you actually want. The second one is just there to be a helper, mopping up and neutralizing that corrosive HCl gas that gets made along the way.
All right, for our final section, we are leaving the flat 2D world of the textbook page and jumping into the fascinating 3D reality of these molecules. We're about to uncover a hidden property called chirality, and trust me, it has some seriously profound implications. So let me ask you this. Here are 2 molecules of a compound called carvone. They have the exact same atoms, connected in the exact same order. The only difference between them is that one is the perfect mirror image of the other, just like your left and right hands. So why on earth does one smell like spearmint and the other one smell like caraway seeds? The answer is this incredible concept called chirality. So what is chirality? Well, it happens when a carbon atom is bonded to 4 totally different things. We call that carbon a chiral center. And any molecule that has a chiral center gets a kind of handedness. It can exist as a left-handed version and a right-handed version. These 2 mirror images are called enantiomers. They are almost identical in every way, but their 3D shape is different enough that they fit differently into the receptors in our nose, leading to completely different smells.
And this idea of handedness is super important when we start making molecules. The way a reaction happens can actually decide the chirality of the product. Take an SN1 reaction. It goes through this flat intermediate, which means the next chemical can attack from either the top or the bottom. You end up with a random 50-50 mix of both mirror images, what we call a racemic mixture. But in an SN2 reaction, the attack comes from the backside, forcing the whole molecule to flip its 3D shape, kind of like an umbrella blowing inside out in the wind. This gives you only one specific enantiomer. So why does this matter so much outside of a lab? Well, chew on this statistic for a second. Over half of all drugs being used today are chiral. And very often, only one of the mirror images is the actual medicine. The other one might be useless or, in some cases, even harmful. And yet, despite that, almost 90% of those drugs are sold as those 50-50 racemic mixtures.
Which brings us to our final, really critical question. We know for a fact that in a common painkiller like ibuprofen, only one of the mirror image forms actually does the job of easing pain. So why is it, along with so many other life-saving drugs, sold as a 50-50 mix? The simple answer is that separating 2 molecules that are identical in almost every single way is incredibly difficult and outrageously expensive. It's a massive challenge for pharmaceutical chemistry, and it leaves us with a powerful thought. Just imagine how medicine could change if we could easily make only the hand we actually need.